Good morning, everyone. We'll start in a minute. Let's wait for maybe 2 more minutes. Meanwhile, Rajesh, if you have any questions, we can discuss.
Yeah, morning, Sanathan.
Good morning.
Good morning. Yeah.
Any questions from your side?
Currently, I don't have experience in data science, but I am applying for a job because I have a previous experience with Microsoft, and I have 20 plus years of experience in other technology like open sources, React, Angular, and so many things. Newly, I'm coming into data science, so I don't have any data science project to mention in my resume. So can I apply for data science because I started floating my resume?
Okay. Yeah, you can. I think there would be no problem as such, but like you can do it only after you're done with this
Uh,
whole curriculum.
yeah, actually, I mentioned I'm undergoing this training
Okay.
like that and started floating. Now, I didn't mention that I have completed or it's currently going on. This is how I mentioned in my resume and started floating.
Okay. Are you mentioning the explicit set of skills?
Sorry?
Do you mention the explicit set of skills? Like for data science, you need, say, statistics, machine learning, maybe, say, working with AWS.
I mentioned only the libraries like
Okay. The list of libraries.
it, NumPy, Panda. So in Python, I have undergoing this kind of studies. This is how I mentioned.
Okay. Okay. Maybe, let's say you apply to a couple more, and then you will definitely get a call because you have a huge amount of experience, right? So the only bottleneck that I see is obviously your ask would be much more, right, in comparison to someone,
Yeah. Yes. Yeah.
right? So that would be a bottleneck for most companies. But if
Yep.
you apply to tier one companies, let's say at Microsoft, right? So they might consider you for that. But for let's say tier B companies, right? In my opinion, you will probably not get a call because
Yeah.
you're so experienced, right? And if you apply for a managerial role, then I think they would probably speak to you. Otherwise, just for a data scientist role, probably not
Yeah.
because they don't pay that well.
Yeah. Yeah.
Let's just be hopeful. Okay, you get a call soon. That's just my opinion, at least.
I'm not applying like normal the people who search for job.
I
So
understand. I understand. I understand. You must be going through your contacts, right?
going through
And yeah, I understand that. But still, right? I mean, think you are 20 plus
yes,
years experience, right? So that's a huge number. Okay, so I can understand it must be difficult. So I would say keep on applying, and probably you get a call soon. And as far as I see it, you'll be getting a managerial position only.
yeah. I was a project manager for my previous company.
So like even when you transition into this data science role, right? That would still be a managerial role for you. So you would be asked to guide a team.
Yeah.
Okay, so my suggestion is maybe complete a few projects as soon as you can. You'll be doing some after this is over, right? After maybe say 1 more week.
Yeah.
We have assigned for another project, Senator. And actually, I was about to talk it like Phone Pay Pulse. We have assigned,
Okay.
and if Rajesh done, like, can I ask a question?
For my sake, go ahead.
Yeah. So, it says like from GUI side, the placement phase was I think it's gonna start from me. So they've asking for the roles like the first role and second role, third role, as per my suggestion. Like, what are all the suggestions that you need from us for the job kind of thing? But basically, I'm from a non-IT background right now, and I'm working as a client relational, which means like I'm working in a non-IT background for a client relation kind of thing to incorporate. So, uh, which roles I can, go, go for? Do you have any suggestions for me like that?
Again, it depends on your ask. So this is what I was discussing with him.
Okay.
The problem, like from his side, is he is, I mean, too much experience and transitioning into a engineer role, like
Hmm.
the person who engineers applications, okay, will not be paying that well. So that's why most companies would be hesitant to hire him.
Okay, but now I have 4 years of experience, and my LPA was also not that high. Like
So
it
yeah,
was ranging
you
around.
can apply for a data science role, a data analyst role.
Okay.
You can also do a bit of data engineering, but you need to learn cloud management skills.
Okay.
Okay, so you need to work. Maybe you can acquire these skills through that GUI premium courses that are there, right?
Mm-hmm. Okay.
Get certified, work on say AWS or Azure,
Mm-hmm.
and then you can apply for those as well, and maybe learn Tableau or Power BI.
Yeah. Okay. Sure.
Okay, and
So I can apply for data scientist, data analyst, and then the data engineer,
data
right?
engineering, yes,
Okay.
but for data engineering, you need to learn some additional skills.
Okay.
For data analyst, I don't think you need anything else. Maybe
Okay.
a little bit of AWS.
What about
Okay.
for ML engineer?
For ML engineer, you need a lot of other things. So maybe I can mention those skills. So you will need maybe a solid foundation in deep learning. So you need to have computer vision. So a good rigorous hands-on on PyTorch or TensorFlow. Okay, you need to be well versed with all different kinds of neural network models that are out there. So maybe let's say if I just summarize, right? Start from artificial neural nets, go to convolutional neural nets, then maybe jump to encoders, decoders, then go to time series forecasting models like LSTMs, RNNs. Then you jump to maybe say integration of these models for specific applications, like for image captioning. You can combine any CNN with LSTM, RNN. If you want to go a little bit more advanced, so let's say you want to go for AI engineers, then you need to learn what are transformers, because they are quite a rage right now. So for learning transformers, you need to be aware of models like, so I'll just tell you the names of some algorithms. Like you need to learn about different variants of attention. And you must have heard of the term BERT, BERT. Anyone? No one?
No, Santa. No.
Okay, so this library is there, which is called as Hugging Face. There's a company by this name, and the library is also by their name. So this company is gaining more and more traction. So before OpenAI became so successful, right? BERT was like the Hugging Face was like the shape was the face of AI. Okay, and OpenAI is not doing that well right now. It's not profitable as such. So I think after a while, these two libraries or these two companies, Hugging Face and OpenAI, whosoever advances, right, whosoever takes the next big step, will become the face of the AI. So OpenAI is going to come down soon. So people have found the limitations of ChatGPT, or you can say wherever it can be specifically applied. And so no doubt there is like a huge potential. I mean, you can apply it to so many applications. However, it is going to come down soon, and maybe Hugging Face will rise up again. So check out this library, Hugging Face. Maybe I'll show you when we are doing NLP, right? So I'll show you how to use some deep learning models for NLP applications. So I'll use this library, Hugging Face, maybe some models from it, and just to show you. So you need to go that far, okay? If you want to become an AI engineer, you need to be well versed with how do you process medical data. So you need to have a good understanding of MRI, CT. When I say good, means good only, not extensive. You need to know about, say, X-rays. So medical imaging is also a little bit needed when you dive into this role of ML engineer and AI engineer. Ultrasound as well. You need to know how to process signals, how to quantize signals. So these are some, and obviously a good amount of data, I would say ML model deployment as well. So you should know about techniques, for example, Heroku, Flask. You would be doing Streamlit, right, nowadays?
Yes.
You would have used Streamlit. So like that, there are alternatives. So Streamlit is kind of free, right, and open source, and you can use it. Right? You're not paying anything for Streamlit, right? If I'm not wrong.
Yes.
But there are other, I mean, you can say paid libraries, which many people use. Heroku was also free not a long while back, but now they have started charging for it. So you need to know how to deploy models on websites. So these are the things like how to build a pipeline, production pipeline, CI/CD pipeline. These are the things that will take you to this ML engineer or AI engineer level. Just to name like the most prominent skills. Obviously, like per company, these skills can vary slightly. However, the overlap would be what I have just suggested. So if you can gain these additional skills, you can apply for these other roles as well. I believe if you have taken note of it, that's fine. Otherwise, you can just rewatch this and maybe jot it down. Or anything else I can help with?
Yeah, Dinesh, you can even try BA positions.
Actually, I was about
business
to
intelligence.
business
analyst.
analyst.
But for that, you would need Power BI, like the Power BI tools.
I have that course in here also, and in my organization also I have that Power BI and all those. So I'm looking actually like actually now I'm working as a senior process excellence guy. So I didn't know like now how my new journey is going to be, because in here like I have different roles and responsibilities. Like I only work on management side, but I don't know like when it comes to data analyst or data science.
Just apply. There is no harm in applying. Okay.
Yeah.
Let's say you get in, then you will learn like the day-to-day routine of what you need to do.
Sure.
There's learning involved as well, right?
Sure.
Yeah, there are like see, I've just quoted the essentials, right? See, there are analysis jobs in every area.
Yes.
It's like Rajesh mentioned, like
Yeah.
business analyst, right? You can go towards finance analyst, right? There's also So specific analyst positions, right? In particular domains, you can always apply, but you need to have a background in it. See, currently what we are doing is on generic data sets, right? It's not specific to a domain. So if you have a background in a very specific domain and to learn these additional skills and apply it on some of your data sets,
Sure.
that would make
Actually, I'm from a medical background right now. I'm working in a US healthcare and yeah.
so why don't you use one of those data sets and maybe build a nice application out of it? You have learned essentially the skills for it, right? Or you're learning, let's say that.
So like I'm from a US healthcare industry right now. So
Maybe you use one of the medical data sets and then you can apply for roles that involve medical imaging. But you need to then go with computer vision a bit.
okay.
Okay, so you can directly apply for. So see, there are niche roles as well. I will tell you this. So all the skills that you have learned, right? Like say SQL.
Yeah.
Do you know that there are roles like SQL engineers, SQL developers?
Yeah.
There are those.
I
as well.
do.
They will not pay that well though, because they are niche roles. Okay, so think about NoSQL. So you will have roles for that also. So people only do that. There is a tool like tool called as Informatica.
Okay.
It's a paid tool, quite expensive. But if you can, let's say, learn through an online course, okay, about that tool, there is a huge demand for that in service-based companies. So companies like TCS, Infosys,
Yeah.
they pay a good amount of money. Though it may you may have heard that okay, they don't pay that well. But
Yeah.
if you have a good understanding of these tools, it's an ETL tool essentially.
Sure. I used to see a lot of referrals for that. Just now only I'm coming to know.
Okay, no, there is a huge demand for that.
Is
Okay.
Informatica still in demand? Because I worked on Informatica
Okay.
2010.
Yeah, it is used still. I'll tell you about my sister. She is a team lead in Nagarro right now. Previously, she was at Infosys, and before that, she was in TCS. So her transition, I'll tell you. Okay, she did her BTech in electronics,
Okay.
and she knew only SQL.
Mhm.
Okay, and because she had that electronics and electrical background, so she joined TCS at a package of around 4.5. Working there for almost 3 years. She worked on Informatica only. Then she transitioned to this Infosys. After 3 years, she did switch a couple of times in between, but like majority of her, you can say, time was spent in TCS. A couple of internal transitions were there. So I don't know if you know of the company Bira, the beer company. Have you heard of it?
Yes.
So she did work there as well for some time in the IT sector only.
In Informatica, like on Informatica tool itself?
Informatica only. Yeah. So so her role was on Informatica only, mostly. Now, I mean, so when she switched to Infosys, right, after working for around 4.5 years, so her package was like 24.5 lakhs. And then when she switched to Nagarro, it's close to 30 now. She switched very recently. So
I took up this course just because I was looking for Informatica job. I have 7 years of experience on it, but I have a career gap, and then I could not find any Informatica related. So I thought of upgrading myself.
I'm just suggesting that is a good tool to, it's still in demand. Okay, and they keep on updating that tool. Okay, so she's in a managerial role right now. I mean, so whatever mess ups the other people do in her team, she's the one who takes care of all of that. And people mess up quite a lot. Let me tell you this.
Yeah, that is actually, oh God.
Two-way shift, so she works late nights. Okay, so I mean, the job is not very friendly, like from a healthy lifestyle perspective. But I mean, she's happy. So it's all going good. It's all going good. I transitioned from academia, from industry to academia. I didn't like the roles as such. I worked in roles like applied researcher, applied scientists, and then I kind of transitioned to move here after my marriage. So Now, me and my wife, we both work and we consult for a lot of companies though. But we keep ourselves updated quite a lot.
So now you're a consultant.
No, I am a consultant, but that's like a freelancing job for me. But
Oh, okay.
I'm a faculty at a subsidiary of Tech Mahindra.
Okay,
So
okay.
here I teach Tech Mahindra professionals and also masters and doctoral students of Mahindra University.
Okay.
I'm trying to move to Jammu. Let's see if that pans out. I've applied to IIT Jammu. Hopefully, we'll get a call from them in some time. And if everything works well, like if my wife also gets selected, we'll move there. We
Sure,
like
sure.
government jobs to come here.
So right now you're
So
located.
Sanatan, will that not be a conflict of interest from the same family, two people in the
Yeah.
same?
So that's why we are only applying to see when we started applying, right? There were many. We started applying to IIT Patna first. So as of now, we don't have a marriage certificate, so we don't tell.
So that will save you.
Yeah, we don't tell. But now we have realized, okay, why to hide this information? So we reveal it and we kind of talk to the director first. So if there is there is no constraint as such, then we apply.
No, usually like the top management, they don't prefer two people from the same family.
And we are in the same department.
Wow.
Okay.
So it is a conflict, and it was there in many places that we applied to. We got selected in all of them. And then they said, okay, one of you can work here, another one in another organization. So we came here in Hyderabad. We are actually from the north, from Chandigarh. And my wife is from Delhi NCR. And we are in Hyderabad right now. So you see, that's very far away. So came here because Mahindra was so kind to us. So we spoke to some of the authorities at TechM. Have you heard of CP Gurnani? No?
No.
CEO of TechM. No? Okay. Anyways, so he was kind enough to offer us. So we left our government jobs, and it happened just before the COVID outbreak.
Oh, you have left your government job.
Yeah, I was working in Tech Chandigarh as a faculty back then.
Okay.
So PEC is a renowned college. It's much better than some of the NITs in that region. And my wife was in IIIT Dharwad, and we kind of left our jobs. So because it was COVID outbreak, then no vacancies were there in either of the institutes. So then we kind of realized, okay, wherever we get a job, we just go there. And now we have realized, okay, there is a dearth of some good quality students here. So let's move to some IIT and probably recapture our heydays. That's the plan.
Sure.
So Sanatan, one last thing on Informatica, like in our ERP circles, we use Informatica as a middleware. And like in our circles, the grapevine says that Informatica is going to sunset very soon.
Oh, it depends on, see, if your company is transitioning from that particular software to something else.
No, it's like a general view in the ERP circles.
Is that so?
Yes, Informatica is going to sunset very soon.
Again, see, it's like you have to give me a timeline, okay? See, technologies don't die very soon. It takes time. Okay, it takes time. I can understand that because the tool is so expensive. Maybe somebody has found any like alternatives, and the company will then switch to this other or some other tool. Okay, but from my perspective, keep this in your skill set, and you can definitely see there is no harm in anything, right? And the tool will not require you to spend a lot of time. I think you can cover the whole thing in a matter of say 8 to 16 hours. It depends on how fast you can understand things, right?
Totally.
So if you can just go through any online course, understand the ETL and the ELT framework that Informatica works on. Maybe do a little bit of grind on SQL. And
It comes as part of data engineer.
yes.
Oh, Informatica is okay, fine.
It's the whole thing. So you have skills. I mean, you will not be working on the whole thing, right?
Yes.
You'll be working on one specific aspect of it. Informatica is like an integration of different things. So let's say you'll be just asked to manage the SQL tables, like the databases. Okay. So you'll not touch any other aspect. Okay. Somebody will be working on the extraction, the transformation side. So it's not one person who works on the entire tool.
So Informatica is not like Jira, right?
No, Jira is a development framework.
Okay. Because I was asking about. Okay, fine. Let me dig in about it then.
All right, we have spent, I think, 15 to 20 minutes talking about this. Maybe we'll have this discussion in last class. I think we'll have some spare time on this.
So, and Sanatan, like just before you start off for the day, see, like what I heard from many of our friends on this platform, like today, what I could infer is like there is no proper definition or there is no proper understanding of like which roles to pick up, like which way to go. Say, for example, if I'm a SAP guy, like I'm an MBA finance, so like there are 7 to 8 modules here in SAP ERP. So like being a finance guy, I can go ahead and choose like SAP FICO, which is finance and controlling. So there's a proper definition and proper understanding of like where to go, what to do. But unlike here, there's like a lot of chaos and confusion, like as to where to go, what to do.
Like when you join a company, let's say if you're talking about promotions, right? I don't think there's a confusion as such. Like but let's say if you need to transition, then I believe there must be some. Yes or no? But you typically transition to another role which has the same prerequisites, right? And maybe a few other skills that you don't have that you will learn. So it's the same here as well. Then the only thing that I mean, the way I see it, you may have a different name. You may see a different name for let's say for your for a position which is, let's say, higher than yours. Okay, another company might be calling it with a different name, but there is a proper structure for it. So just like in your
JD would be the same, right?
Is right. Yeah. There is a hierarchy, right? So I frankly don't see it that way. There is a proper hierarchy. Even in your case, right? You will be, let's say, if you join as a data scientist, let's assume. So you will have DS1, DS2, DS3. Just like software developers have this hierarchy, right? SDE1, SDE2, SDE3.
Right, lead principal, so on and so forth.
Yes. So as you get acquainted with more and more skills, and let's say you have spent a decent amount of time working on a specific technology, right? They push you up. There is a hierarchy as I see it. Maybe when you transition to some other company, the name would become different. But I don't see it that way. I mean, the way you communicate it. So from my perspective. Okay,
that's my understanding, maybe.
No. I mean, you are talking to different people, right? People have opinions.
Right.
My opinion is like there is a hierarchy for sure. Okay, there is a hierarchy for sure. Anyways, see, I didn't want to I put you down in any way. Don't take it the wrong way. Okay. As I see it, like, yes, there is a hierarchy for sure.
Well, I just pulled across like what I learned in the past 5 years of my professional experience.
Could be. See, obviously, I have not been in touch over the last 6 months or so. So I can't deny this unless I do a little bit more research about it. But frankly, I do see a hierarchy. Okay, I do see a hierarchy. Okay, so maybe let's say I kind of agree to disagree. Okay. Anyways,
Point taken.
Okay. Let's just talk about today's topic, which is clustering. So again, this is an unsupervised learning technique. I'm sorry, guys, like for the other people, I don't know whether you found the conversation useful or not. But take it from me, these conversations are required. Okay, so it's again an unsupervised learning technique where the objective is you want to group examples. So let's see it from a visualization perspective. Imagine that this is how the data looks like. So you have two features, let's say X1 and X2. So your data set would be given like this. I'm taking a two-dimensional data set so you all can visualize and see. Do you think we can visualize in more than 3 dimensions? Is it possible to visualize the data in more than 3 dimensions? Anyone? Can we plot in more than 3 dimensions?
Visualization is not possible.
Not possible, right? So keep that in mind. Right? I'm doing it in a 2-dimensional scenario because you can see what is happening. In more than 3 dimensions, I mean, I cannot visualize, but the same things happen there also. Okay, same things happen there also. So let's say this is how the data looks like. So this is how the data looks like. What do you see in this data? Some groups, right?
Yes.
Okay. So the objective is if I can find these groups, okay, let's say if I can find these groups, I can do a lot of things. So one is I can make recommendations. I can make suggestions, right? So think about this. Let's say this is a customer. I am looking at the age and say, what do I say? Age and say experience. Okay. So if these two people have the same age and experience, okay, can I say that I can suggest them, let's say, the same jobs? I mean, let's say they all are from the same background. So can I suggest them the same job?
Yeah.
Okay. So like the same idea here. What about this person? What would you call this person? The one on the very top. An outlier. So you can do outlier detection. Or this is also called as anomaly detection. Okay. So these are some of the applications that you can build from it. I'll give you maybe some more, which can be a little bit interesting from like real world standpoint. How do these mobile companies know where to install mobile tabs? Any guesses?
From whichever area they get maximum requests, like request signals.
Which is more
Yes.
densely populated. How do they locate that area? That is what they use. Okay, that is what they use. So they try to group the locations of. So if I give you longitude and latitude locations of like on a 2D grid, if I plot the longitude and latitude locations of where the houses are constructed, okay, or let's say if I give you a Google Earth view of, you can say a particular region, okay, a particular area, can you identify just by looking at it visually at what places like constructions are there? So you can make assumptions. Okay, this is where people live.
Yes.
Yes. Yes.
Internally, what you're doing is you're trying to kind of figure out those regions or those sub-regions where there are massive constructions, right? Where people live. So mathematically, how to do that? Okay, that is what the idea of clustering is. I'll give you maybe some more examples. Let's see, you are. Okay, I'll give you a silly example. Maybe it's not silly, but I think it can catch your attention. Let's say you are working in a company, right? And a company typically will have a building, or maybe will rent a building where you will have multiple floors, right? We are talking about a floor, one of the floors. So the question is, like, typically nowadays, like buildings are huge. Okay, so on a single floor, you can have different regions, right? Some
Yes.
regions are for, let's say, relaxing. Okay, maybe say entertainment, like you have table tennis and all that, all those things there. Some regions are where you have employee cubicles. Some regions are where higher authority sits or HR sits. Okay, HR department is. So they are kind of distant from each other, right? Some regions are there where IT people sit, where you get your laptops and all these things from, the accessories and all. So the idea is you want to install some coffee machines. Okay, coffee vending machines, or maybe say some food vending machines. how do you know, okay, where to install those? Do you think there is like a random decision taken, okay, this is where I should install those?
No.
No.
Right. So the intelligence there lies in, if you know the actual locations, can we identify regions which are again densely populated? And maybe for each densely populated region or a fairly densely populated region, I install one coffee maker.
Yes.
Yes.
I do not have like that many resources to give one to everybody, right? Okay. And so just to decide the locations of where to put, okay, you can use this idea of grouping. Okay. And then you can put constraints like it should have at least these many people in the group. So I'll do this. Otherwise, I take the decision like as per my understanding. This is a technique which can help you group. Okay. And then you make the decisions based on the answers that you get. Okay. So in your curriculum, there is just one algorithm, but I'll give you many because they are all required. At least, so there are baskets of these algorithms. You can, so if I say the whole group of clustering algorithms is lying here, okay, you can divide them, you can categorize these algorithms and put them in some baskets. So there are many researchers who have tried to do that. And they have come up with their own categorization. Maybe I'll give you two of them. Two of them are very popular in the community. So one is where, so it is based on, okay, let me ask you this. If you look at this visualization, how many groups do you see?
4.
4, right? Now, let's say I have 2 coffee machines to install. Okay. So can you give me a generic idea of what you would do?
Again, out of these 2 groups, I can see which 2 groups are close by, so I'll combine.
One way to do it, right? But would you leave out any person?
No.
No.
Fair, right? Okay. So maybe what you'll do is you'll try to identify the best 2 groups that you would have. And let's say look at the centroid of those groups. So this is where the centroid would be, right, for one. And this is where the centroid would be for the second, close to the dense regions. Yes or no?
Yes.
And you can install these coffee makers here in the center location, the average location of all the people in that group. So what we did is like, we thought of an application, we thought of a clustering algorithm, which can figure out the clusters automatically, okay, based on the design, I would say. So the idea is if you can pre-specify the number of groups. Okay, so do you realize there are applications for it? See, one idea is I automatically find the number of groups. Which do you think is better, automatically or pre-specifying the number of groups?
Pre-specifying the number.
Is this better, right? Okay, because then you can do something for every group. You would know how much resources you have, right? And for every group, you can dedicate one resource. So if you have K resources, you find K groups and then dedicate one for every group. So this is where most of the work is in the community. Even let's say if you ask a naive person, they will say that automatically finding the groups. They will say that this is more important. Okay, this is not that important. So based on the design of the algorithm, like if you can pre-specify the number of groups, all right, there are algorithms for it, and there are algorithms which can automatically find as well. Okay, so we'll see some algorithms from each basket. Another categorization which is popular is this. So depending on what you say is the assumptions of the algorithms. So one of the algorithms that you will see is density based, as we are talking about. So kind of connecting dense regions with the help of non-dense regions. So look at it like this. Okay. How many clusters do you actually see?
Can be even one cluster because
It's only one cluster, right? If you think about it, these are non-dense regions. Can I say that? This is a non-dense region trying to connect 2 dense regions.
Yes.
Okay, but somebody can view it maybe as 3 clusters. somebody can view it as one cluster. Does that make sense?
Yes.
Yes.
So the idea of these algorithms would be that you try to connect dense regions with non-dense regions to form a chain-like structure. Okay. So we will see one algorithm from this category. Then there is something called as partitioning based, where you the example that I gave you earlier is partitioning based. Okay, where you partition your data into regions, okay, which are non-overlapping. So if you look at the partitioning that I have done, is one sample belonging to multiple regions? Look at any one sample. Is it belonging to multiple regions?
No.
Okay, one region only, right?
Yeah.
Okay. So the idea is you partition your data in a way such that under certain assumptions, we will talk about those assumptions. Those assumptions are kind of common to most algorithms. Okay. So you want them to be well separated. Okay. You want them to be well separated, but every point will go to like one of the partitions. Okay. All right. Then there is something called as okay, I'm missing this just a second. Hierarchy based. Do you remember a decision tree? What does it do? It partitions your data, right? And you get at the nodes, you get a partition, right?
Yes.
Can I say that decision tree is kind of also doing that? It's getting the partitions of your data. If you think about it, every partition is non-overlapping, right?
Yes.
But it gives you a hierarchy-like structure. How you came to that partition from the parent. Yes or no? So we will see one such algorithm from this basket as well. Okay. So there are algorithms which kind of find clusters in a hierarchical manner. And then there is something. So all of these algorithms that I've talked about, they are called as non-overlapping. Non-overlapping meaning that one sample belongs to one partition only. Yes or no?
Yes.
One sample belongs to one group only. It cannot belong to multiple groups. However, there are algorithms which are called as overlapping algorithms, where one sample can belong to multiple groups. And don't you think that is kind of true? Do you think you associate yourself with one skill?
No.
So you inherently have multiple things, right? You're a part of multiple groups. Maybe you're a part of HR group. You're also a part of table tennis team. You're a part of football team. You're a part of cricket team, right? So you are a part of many teams, right? So the idea is, if a sample can belong to multiple groups, can I give it a probability score? Okay. So if there are k groups, then every sample will have how many values? K values. And each of the values will be a probability score. So if for the first cluster or the first group, you say you are 10%, there is a 10% chance that you belong to this group. There is a 50% chance you belong to group 2. There is a 10% chance you belong to group 3. So for every cluster, for every group, there would be a probability score. And the sum of the probabilities would be equal to 1. So does this make sense? So it's a probabilistic algorithm essentially. Okay, it's a probabilistic algorithm. There are non-probabilistic algorithms as well, which simply tell you directly, okay, whether you are part of like this cluster or not. Okay, so given k clusters, which are the clusters that you are a part of? Okay, and you can view it from a probabilistic perspective as well. Does that make sense?
Yes.
Okay, this is not a part of your curriculum. Even only this is a part of your curriculum, by the way. And there is only one algorithm. To understand this, you have to go a little deeper. So I'm not going to cover that. I don't have that much bandwidth. But if time allows, I'll cover one of them. Okay. So there is in each category, there are literally hundreds of algorithms. I'm going to give you the most popular one, but this category I'm not going to touch. Okay. Because this category requires advanced maths. And there is no mention of the prerequisites in your curriculum. So I'm not going to touch it. But I'm telling you this exists. So if in an application you require for a point that there are multiple clusters and you want to associate a probability score or a value that, okay, this belongs to this cluster or not, say 1 or 0, there are also clustering algorithms for it. Okay, so this I'm not going to cover. Okay. But if time permits, I'll cover maybe one aspect of it. But at least we'll tell you the name of the algorithm and we'll show you the implementation. Okay. All right, so let's start with, by the way, there is just this one. I'll repeat this. There is only one in your syllabus, just one, which is a non-overlapping algorithm. Okay. And there is one more popular categorization, which is like outlier based. So can a clustering algorithm determine outliers or not? Okay. So there is one more. So many researchers have given their own categorizations. So you can think of it as some of the clustering algorithms can identify outliers and some of them cannot. Okay. So the example that I gave you, where you are trying to find two partitions, do you think you have any outliers? The red clustering that you see?
No.
No, right? So there are no outliers as such, but you can modify it to identify outliers.
Yes.
So, okay. So just for your knowledge sake, there is a library called as, though it's not again a part of your curriculum, I'm just telling you this. Interested, check it out. So my job is to tell you. If it's there in your curriculum, I'll cover it. Otherwise, please don't expect that from me. There is one library called as PYOD, Python Outlier Detection. Okay. What this library contains is almost, I think, 18 to 20 algorithms. Just like we have seen PyCaret and Lazy Predict, right? For supervised learning.
Yes.
Remember it or not? Okay. So similarly, there is a library called as PYOD, which can identify outliers. It has implementations from many different algorithms. So some of these algorithms are actually clustering algorithms, and they have been modified to determine outliers. Okay, it's a good library. I request you to please check it out. Not a part of your curriculum, and you cannot, use it like PyCaret, where it will run 20 algorithms in one shot. So this is like sklearn, where you have to call one method at a time. Okay, but an interesting library to have in your CV. Okay, some people who are essentially trying to determine frauds. So fraud detection specialists, they use it. Okay, so banking frauds, or you can say financial frauds. Okay, people, those kind of people use it. Okay, all right. So let's start with one of the algorithms. So before I start with say any algorithm, let's discuss some characteristics of a clustering algorithm. What it should have. Okay, what should be the ideal properties of a clustering algorithm, and we will also understand what should be the input to a clustering algorithm and what should be the output, because that is something which is necessary. Okay, and how do we validate a clustering algorithm? How do we evaluate the performance of a clustering algorithm? Okay, these are some things that you should know about. These are interview questions essentially. Okay, let's take a small example to illustrate this. So you have two features. Okay. So this is just to illustrate. How many clusters do you see?
Two.
Two, right? Okay.
Yeah.
This is one and this is one, right? Makes sense? Okay. Why is this not a good clustering?
Because the samples are far away. Like the difference in them, the distance.
No, say the samples, right? You have to talk about the groups now. Okay. So think about this. When you want to do clustering, right? What can you say about the distance between the groups? It should be high or low.
Between the groups, it should be high.
Okay. So I'm going to define this distance as between distance. Okay. So can I say between the clusters, the distance should be high? Okay.
Yes.
You call this as a cross distance. If you have understood this concept, this is important. Okay. To understand the working of any clustering algorithm, this is what I seek for a good cluster. Okay. And what about the distance within a cluster? Should it be high or low?
Low.
Low, right? Do you realize this? Okay. So that you can call it as within distance. So some people also call it as across distance as interdistance. Okay, many people use different names. Okay, this is called as within distance, which is the. Am I making a mistake here? Just a second. This is called as intra distance. Okay, and this should be low. All right. I'm going to show you a proof that. Okay, do you think that both the things are kind of similar? Within distance should be low and between distance should be high. Or are they different aspects?
Yeah. Dependent on each other.
There is a relationship between the two. So I'm going to show you. Do you want a statistical proof for it? Okay, if you try to minimize within, across will automatically get maximized.
No.
Or you can take it as a fact. Shall I show you on a small example that, okay, this will hold. Shall we do on a small example?
Okay.
Okay, just to understand this. Okay, just to understand this. Okay, because see, nobody is going to ask you for a proof of it. There is a whole dedicated proof for it, but I'll show you on a small data set. This will hold for sure. Okay, so that you have an understanding of why this is true. So if you act, what I'm saying is, if you take care of one of these things, the other thing will automatically happen. Okay, the other thing will automatically happen. Let's see why. Imagine I'm taking these 6 points. Let's say x1, x2, x3, x4, x5, x6. Okay. So I'm going to use one of the clusterings. Okay, please see this. I'm not saying this is the ideal grouping. Okay. What is it that you want to find? You want to find these two groups, right?
Yes.
You want to find these two groups. Okay. My purpose is to locate them. Okay. I'm going to show you that. Okay. Let's say that this is one group and this is another. My purpose is to actually find these red groups, which I've already spoken about. This is the final output. Okay. How can I reach to this? How can I reach to this red cluster? By minimizing what?
The distance.
Minimizing the within distance, right?
Yeah.
The intra distance. Okay. And the other way to look at it is by maximizing what? The across distance.
Yes.
So I'm going to start with this purple clustering, and just to show you something, okay, that if you try to minimize the within, okay, you will actually reach this red. Okay. Even if you minimize across, you will actually reach to this red. Both the things are the same. That's what I want to prove. Okay. Let's see this. Why this thing holds. Okay. So,
you're saying that if I minimize the purple or red, however, I'll
if you so this is one purple clustering that you see, right? Where these 4 points belong to, say, purple cluster 0, and these 2 points belong to purple cluster 1. Does that make sense?
Yes.
I'm saying that somehow I will update this clustering and will lead to these red clusters. Okay.
Okay.
So I'm saying that I will update the answer. Okay, I'll update myself. So currently, let's say you are in a stage where you have found that, okay, x1, x2, x3, x4 is belonging to one cluster, and x5, x6 belongs to another cluster. I'm saying that let's try to change this assignment and make it better. Okay, how do I make it better? By minimizing the within distance, right?
Yes.
So can you see that in the red, the within distance is even smaller? Yes or no?
Yeah.
It's much tighter, right? X4, X5,
Yes.
X1.
Yeah.
I want to find that, right? Do you think that if I just show you a visualization, you as a human can do it, right? But how would the machine learn it? You have to make a algorithm for it, right? Yes or no?
Yes.
So I'm going to show you that what that algorithm will do. It will try to move from this purple to red by minimizing the within distance. Okay. So if you try to minimize the within distance, or if you try to maximize the within distance, both will work. That is what I want to show you now. Okay.
Okay.
So both the things are equivalent. That is the purpose of showing you this. Let's see how. Okay. So I have 6 points. Okay. Let's say I was computing the distances between these 6 points. How many pairs will I have? Anyone? I want to compute the total pairwise distance between all the 6 points.
Pairwise for 6 would be 6 choose 2.
How much?
6 choose 2.
No, that is how much? 15 pairs. Does that make sense?
Yes.
So one pair would be x1, x2, one pair would be x1, x3, one pair would be x1, x4, x1, x5, x1, x6. Can you write all possible pairs? You can do that, right?
Yeah.
Do you want me to write all of them, or you can think of okay how to write them?
Can be done.
You can write them, right? Okay, you can count that. Okay, it will be like 15 pairs in total. Okay. Now for the purple clustering, okay, I want to figure out the within distance. Okay, for the purple clustering, please keep that in mind. So how many clusters do I have right now? 2 clusters, right? So I'm interested in finding the sum of within distances. So I have 2 clusters, 2 purple clusters. So let me find out the within distance of cluster 0 and within distance of cluster 1. So you're only looking at within the clusters. Okay. So how many samples are there in cluster 0?
4.
So how many pairs will be there if you count the sum?
0.
How many pairs would you consider for finding the within distance of cluster 0? There are 4 samples in it.
Yes.
So how many pairs will you consider out of those 4? 4 choose 2. Okay, let me ask you, find the within distance of this cluster 0. How would you find that within distance? For 6, if I gave you for all possible pairs, you said that okay, it would be 6 choose 2. So are you not measuring the distance of every possible pair?
Yes.
So now you're looking at within a cluster. So within a cluster, how many samples are there? 4, right?
4, yeah.
So for you have to count all the distances. So how many distances would you count? 4 choose 2, right? Okay, so this would be 4 choose 2. What is that? 6. Keep that in mind. Okay. And for the other cluster, cluster 1, how many pairs would you consider?
1 pair.
2 choose 2, which is 1 pair, right? Does this make sense?
Yeah.
Okay. Let's see the across distances. Okay. So there are 2 clusters only, right? So if you want to do the across distances, one sample of cluster 0, let's say x1. Okay, let me use a different color. One sample of this cluster 0, you will compute how many distances with respect to the other cluster.
1.
X1 will be computed with respect to with respect to the samples of cluster 1, right?
Yes.
Okay, so how many distances will be there with respect to x1?
2 choose 1 we'll do. So we'll do x1, x5 and x1, x6.
Makes sense, right? This is for across.
Yes.
Okay. What would be for x2? The same thing, x2 with x5, x2 with x6.
Yes.
So if one has n samples and the other one has n samples, what would be the total number of pairs? M into n. This has n samples, let's say, and the other one has n samples. So how many total distances would you consider? M into n, right?
Yeah.
Make sense? Okay. What is that number here?
4 into 2. So
8. Okay. So you have a total of 8 pairs, right? Does that make sense? Yes or no?
yeah.
Okay. Now listen to this carefully. The total pairwise distance is nothing but sum of within distances plus sum of across distances. Okay, if you're not convinced, I want you to carefully visualize this. What I'm saying is every possible pair that you can make out of all these pairs, it will either contribute to within or it will either contribute to across. There will be no pair which would be missing. Do you agree with this?
Yes.
Do you see that the sum of them is what? 8 plus 6 plus 1.
15.
Do you see that both the things are equal?
Yes.
Okay. So every pair, do you see? Take any pair from all the 15 pairs. Do you realize that it is contributing to either sum of the within or sum of the across? It's not contributing to both of them. Will it ever be possible?
No.
No, right? So do you realize that every possible pair contributes to only one of them? And there is no pair which is missing, right? Yes or no?
Yes.
This is the important part of this, important part of this proof. Okay. So both the things are actually equal. Okay, sum of within plus sum of across is equal to total pairwise. For a given data set, can I say this total pairwise would be a constant? For any given data set, if I give you given data set, you have n samples in it, you compute n choose 2. It will be a constant, right? Some value, some distance sum. Yes or no? It will be like a scalar value, right?
Yes.
Is this going to change?
No.
No, right? It's a scalar value that you will get, okay? A constant value, okay? But what can change is what? You can change this within and you can change this across. Yes or no?
Yes.
If I would have given you red sampling, okay, the red clusters, how many pairs would be there in sum of within?
Within would be
3 choose 2 and 3 choose 2, right? 3 choose 2 is 3. So 3 plus 3, 6 pairs would be there in within. And how many would be there in across? 3 into 3, 9. Do you see that sum is still 15?
Yes.
Okay. Do you still see that the sum is still 15? So whatever, so my intention is to go to that better clustering, right? So how do I go to that better clustering? Either by reducing this, okay? So if I try to reduce this, what will happen to the other quantity?
Increase.
It will automatically increase. Why? Why? Because their sum is a constant. So if you increase one, the other one gets decreased. If you decrease one, the other one gets automatically increased. So do you realize that if I want to do clustering, I can either minimize the within distance, or I can minimize, or I can maximize the across distance. Does that make sense? Yes or no? So this should be the objective of any good clustering algorithm. Both are equivalent. Yes or no?
Yes.
I just try to prove this for you guys. Okay. This is the kind of understanding that you should have. If you do one, your objective would be achieved. Okay. So if you do one, okay, you can go from purple to red. Okay. All right. Let's see how it works in action. Okay. We will see a visualization which will help you realize, okay, this is what will be actually happening. All right. Now, some key things that we need to understand. Okay. What should be the input to a clustering algorithm? So what would you give to the as an input to a clustering algorithm? The data. No. The data. The data. The data, right? You will just give this data, right? Yes or no? You'll just give this data. Okay. So input is the data. Now let's say your clustering algorithm belongs to one of those categories where you have to pre-specify. So what else will you give as the input?
Number of clusters.
Number of clusters that you want to identify. Yes or no? Okay.
Yes.
So what is that? A hyperparameter?
Yes.
That can change, right? Depending on the data set that you have. Okay. It's a number that you are providing, right? So can I say the hyperparameters also? So one is the data and the other one are the hyperparameters.
Yes.
It's the same thing as supervised, right? You provide some hyperparameters, right? Okay. So hyperparameters could be the number of clusters or maybe something else as a constraint. Yes or no? Okay. And what should be the output? So what is it that you want? You want to identify if a sample belongs to which category, right? Which group?
Yes.
Yes or no? So for every sample, you want to do it.
Yes.
Okay. So if I want to do it for every sample, how many outputs do I have? In this case,
12.
12, right? So output will be equal to the number of samples.
Yes.
Okay. For every sample, I want to know to which category it belongs to, right? So it will be equal to n, right? If there are n samples. Does that make sense? The size of the output will be equal to the number of samples. Yes or no? So let's say this is for sample x1. Okay. This is one group. This is another group. Let's call this as cluster 0. This as cluster 1. Okay. So x1 belongs to which group? 0. Does that make sense? Okay. Let's say this sample, this is x1. Okay. Let's say this is x2. x2 belongs to which group?
0.
So you will write for x2 also, this is a 0. Okay. Let's say if you look at this, this is x3. So x3 belongs to which group?
1.
1. So do you realize that for each sample, you are essentially writing a number, the group number?
We're doing classification.
No, it's not classification. It's the group number that you are assigning. See, in classification, I know the categories, right?
Mm.
So, okay, let's think about this. If you pre-specify the groups, you will give a number, right?
Yes.
Let's say you are specifying, I want to identify 4 clusters or 5 clusters, let's say. Okay, I want to identify 5 clusters. So K is 5. So in Python, indexing starts from 5, right? 0, right?
Yes.
So what are the possible outcomes? 0, 1, 2, 3 up to 4, which is like K minus 1.
Yes.
Okay, so can I say that every sample will belong to one of these categories, one of these groups, right? So it's similar to classification in the sense that the number that you're providing, it is from 0 to K minus 1. In classification, what we were trying to do, we were trying to put one sample in each basket, right?
Mm.
In each category.
Yes.
The concept is the same, but we don't have an explicit category here to assign. Okay, keep that in mind. Because there are other algorithms also which automatically identify the groups, right? So do you think for them you will know what K is? No, right? K will be incremented as the algorithm finds more and more groups, right?
Yes. Yes.
Yeah.
Okay, so it is not fixed here. In classification, the groups are fixed, the categories are fixed. Yes or no?
Depending upon the data, the K will change.
K will change. Okay, depending on the data, the K will change. Okay, and the algorithm also, the K will change. Okay, but the idea is you will have n outputs. Okay, you'll have n outputs up to say x12. Okay, up to x12. Okay, up to x12. So for each sample, you have a category label. Okay, you can, instead of calling it as category label, you call it as cluster label. So this output is also called as, by the way, cluster labels or simply labels. Or simply labels. Okay. Some people also call it as cluster assignments. It's also called as cluster assignment vector. Some people also call it as cluster membership vector. Okay. So because it tells you the membership of every point. Okay. It's also called as cluster membership vector. All right. So these are the terminologies used by different people. So keep that in mind. Okay, keep that in mind. So shall we do our first algorithm? Shall we do our first algorithm? Okay.
Yeah.
Okay. Before we start, right, I have a small question. Or rather, let me start with the simplest one. So the algorithm is called as k-means. Where did we see k-means before?
Smart.
Smart. It was a type of a technique which would generate synthetic data for you, right? K-means with Smart can help you identify where to generate new samples. Okay, but today I'm going to discuss k-means. It's a clustering algorithm. Okay, it can identify groups. So do you remember in k-means Smart what we were doing? We were identifying groups, right?
Yes.
And if in a group, if a minority example had, you can say the neighbors of the minority example were majority, we did not create a synthetic sample for it, right?
Yes.
Okay. So here, this will act as a clustering algorithm. Okay. There also it was acting as a clustering algorithm to identify the groups. Okay. Let's see, how does it identify the groups? So before that, let me talk about what type of algorithm it is. It is the partitioning based algorithm. It helps you partition your data into explicit K groups. This is the number of groups. I'll tell you why it is called as k-means. Just in a bit, you will realize this yourself. So it's a partitioning based algorithm. You have to pre-specify the number of clusters. You have to pre-specify the number of clusters, the K value. Okay. So if you say that the cluster is, and the number of clusters is K, what would be the range of cluster assignments?
K minus 1.
Up to K minus 1. Okay. So you'll go up to K minus 1. Okay. These will be the explicit cluster labels. Okay. All right. All right. So this algorithm doesn't identify outliers. Okay. But you can modify it to identify outliers. I'll talk about how to do that. Okay. It's very simple, by the way. Okay. It doesn't identify outliers. It doesn't identify outliers. Okay. So let's see how it works. So I'm going to, shall I show you a demonstration directly, or shall we see the nitty-gritties of this algorithm with some examples, or shall we directly move to a demonstration and understand, okay, this is what it is doing?
Understand and then first see
Okay.
the
All right. Okay. Let's see this. So the purpose of this algorithm is just like any ideal clustering algorithm. It will try to minimize within. If you're minimizing within, you will automatically maximize across. Okay. All right. So the algorithm is actually like gradient descent. Okay. The algorithm is actually like gradient descent. So what does gradient descent do in the beginning? It assigns random values, right, to your parameters. It initializes your parameters, right? So what we are going to do is we are going to initialize, okay, we are going to initialize all these samples with a random cluster label. So give me a value of k that you want to find. Give me a value of k that you want to find.
start with 2.
Okay, let's start with 2. Okay. So you want to identify 2 clusters. Okay. So what are the cluster labels? 0 and 1. Okay, you can call it as cluster 0 and cluster 1. Okay. So I'm saying that you start by just giving a random label to every point. Okay. So maybe if to this point you can say you belong to cluster 0, to this point you can belong to cluster 0, to this point you belong to cluster 0, this you belong to cluster 0. Just say, okay. So if these points belong to cluster 0, so what is the original membership? Like this, right? Yes or no?
Yeah.
Okay. So you start randomly, and let's say other ones belong to 1. Let's say other one belongs to 1. So this is how the initial assignment is. Does that make sense? Okay. See, you can see it visually, right? It looks very nice. Okay. However, there is a possibility, okay, maybe say I say that, okay, this is also cluster 0. Yes or no? Okay, maybe say this is also cluster 0. All right. And only one of the points is cluster 1. Maybe say only this point is cluster 1. So what happens is if you do it like this at random, okay, the algorithm will give you good outputs. Okay, the algorithm will give you good outputs. Like it will actually converge to these 2 clusters. Okay, it will actually converge to these 2 clusters at the end. Okay. However, it will take a lot of time. Okay, it will take a lot of time if you just assign it randomly. So let's do it in a somewhat intelligent manner. Okay, let's do it in somewhat intelligent manner. Let's see how we can assign these clusters randomly, but that too in some intelligent manner. Okay, that too in some intelligent manner, so that the algorithm converges faster. Okay, so that the algorithm converges faster. So I'll just give me a sec. Let me. I have to probably remove some of the things. Okay, just give me a sec. I've been using these slides for quite some time now. Okay. Just give me maybe say 2 minutes. Just give me 2 minutes, please. There's a lot of clutter here. I want to remove this. Okay. All right. Assume that this is the data which is given to you. Okay. Assume this is the data which is given to you. Forget about these 2 points for now. Okay. Forget about these 2 points for now. Come on, this is not working. Just a sec. Just give me a moment, please. One second, please. One second. It's okay. My pencil hasn't. It's not working. Now it's. What is happening? Just a second, please. That's automatically getting removed. This is strange. Okay, now it's working. That was completely strange. Okay. Oh. This is very weird. Okay, let's start. So forget these points. Okay, forget these points for now. Okay, so what we are given is a data set with two dimensions. This is x1 and this is x2. Okay, can you see that you're given a lot of points? These green are the points that are given to you. So this is say point x1. So maybe say this is some say 0.75. Okay, and maybe say this is 1.9. Okay, does it make sense? So you're given a data set like this. So the first point x1 is this is 0.75 and this is 1.9. Does it make sense? Yes, people. Any doubts about understanding this visualization?
Yes, I think got it.
Okay, all right. Okay. So one idea is that I can assign these points with a random clustering label. Okay, I can say this is say cluster 0. I can say this is cluster 1. Maybe say this is cluster 0. I can do that. Okay, I can do that. There is no harm in it. So we are still doing two clusters. Okay, we are still doing two clusters with 0 and 1 as my clustering labels. Okay. So I can assign it randomly. Okay, that is one way to do it, but that will take more time for convergence. So another simple way to do it is this. Why don't we start with two totally random points? So these are the points that you can take anywhere, wherever you want. Okay. So how many clusters I want? I want two clusters, right? So let's say one of the clusters is red. Let's say 1 is red, and maybe say this 0 is blue. Okay. So what I'm saying is start with, so if you are choosing 3 clusters, start with 3 random points anywhere. It could be a part of your data set. It could be even outside your data set. It doesn't matter. Okay. So start with any 2 or 3 points, whatever the number of clusters is. So currently I'm choosing 2 clusters. So I'm going to choose 2 points. Okay. This is called as the starting blue point. Okay. This is called as starting blue point. This is the starting red. This is the starting red. Now, treat these points, okay, treat these points as the centroids of red and blue cluster. Okay, this is centroid of the red cluster. This is the centroid of the red cluster. And this is the centroid of the blue cluster. Okay, treat this as the centroid of the blue cluster. This is the initial that you have assigned. Okay, the mean of the red and the blue cluster. So I have a question. Look at this point. Okay. So what would you assign this point as? Red or blue?
Red.
Red, right? Why?
Distance with red is less as compared to blue.
Makes sense, right? So if you look at the distance with blue and the distance with red, red is much small. So I can directly assign it to the red cluster. Okay. All right. What about this point?
Blue.
Blue, right? Okay. So I'm going to show you a technique which can directly assign these points, okay, in a single shot. Okay, in a single shot. And this actually converges faster because my clusters are kind of well separated. Okay, let's see. So you connect, or maybe I'll show you. So which color should I use? Okay, you connect these two cluster centroids. You connect these two cluster centroids and draw a perpendicular bisector. Okay, draw a perpendicular bisector, the line passing through the middle. Okay, so any point which lies on the left hand side, where do you think it will belong?
Blue.
Blue, right? And anything on the right hand side will be
Red.
Make sense? Yes or no? Don't you think just by using simple geometry, I was able to find two well separated clusters in the beginning?
Yes.
Okay. So this is the advantage that we get if we see, and isn't it random initialization? It is random, right? Because even wherever you put these points, don't you think you will get well separated clusters? But if I pick for every point a cluster label 0 or 1, it would look very weird, right? Yes or no? Some points will be red, some points will be blue. That will look very weird, right? Okay. Let me tell you, if you have well separated clusters in the beginning, the number of steps to reach to the best clustering, okay, it is smaller. Okay. That is why we want to identify well separated clusters in the beginning. So this is one way to do it. So it is still random initialization, but done a little bit intelligently. Okay. So this is how the clusters would look like. Do you agree?
Yes.
Okay.
Yes, sir.
Now, if this is the red cluster, okay, if again this has stopped working, I don't know what is happening. Just give me a moment, please. Is there a lag? Just give me a second.
No lag and all.
No, I'm trying to write. It is not displaying. Just a second. No, it has enough battery also. 1 second. Has enough battery also. Okay, anyways, I just want you to identify this. Okay, let's say, if are you able to see the red cluster? I don't know. My pencil is not responding. My pencil is not responding.
Yeah, we
Yes.
can able to see the picture.
Okay, so if you see the red cluster, right? Okay, and you also see the points in the red cluster. Where do you think the red mean should actually lie?
Red mean would be somewhere like in the
Closer to this dense region, right? The okay, let me see if I can still make it work. See, it is selecting, but I don't know. I am unable to draw this. Okay. It was working earlier, it stopped here. See, on this slide, it is working. However, on this slide, no. I don't know what's happening. Okay. So do you see that? Okay. Anyways, do you realize this? The red cluster and blue cluster should move here. It's like simply taking the average of all the points. So if you take the average of all these red points, do you realize that the red cluster will actually fall here? Where it is highlighted. Here. Okay. My goodness, this is so weird. Still unable to draw it. Anyways, I don't know. I think I need to delete this file, maybe use a new file, because I've used it a lot of times. So the idea is, if you look at this red cluster, right? Or maybe I'll use this, okay, just to demonstrate this. Okay, I'll use this. Okay. You'll get the idea. Okay, the visualization is pretty straightforward though. Let's say these are the points. Okay. I'm starting from here. Maybe say this is red. Okay, and let's say this is, maybe say blue. You can call it purple. Okay. So if you try to connect them and draw a perpendicular bisector, okay, so all these points will be red. Okay, so these will be red and the other ones would be blue. Does that make sense? These would be purple. Yes or no?
Yes.
Okay.
Yeah.
Now, where do you think the red center would lie? Where do you think this will move? This will move here, right?
Yes.
Okay, and where would the purple center move? Maybe slightly towards here.
Close to that person.
Okay, towards these 3 points, right? Because there is more density there. Does that make sense?
Yeah.
Okay. Let's shift it. Okay, let's shift it and see what will happen next. Can you-
below
yes.
to the purple, the below to the purple point also will move towards the density.
No, the purple point is not going to move. Points are not going to move. Only the centroids will move.
Okay.
Okay, the initial centroids that you chose, only they will move. The points will not move. Okay, the points will not move. Okay, so this is where your red centroid is, and this is where this is your red, and this is where your purple is, new purple.
Okay.
So I want you to tell me this. If I again look at this point, okay, if I again look at maybe say this point, to which centroid it is closer to now?
Red.
Red, right? So this will become red now.
Yeah.
Okay, and will there be any other changes?
No.
No, right? So this has become red. Okay, so after you do this, okay, there will be no other changes, right? In any other point. Do you realize this? Okay, rest will remain purple and rest will remain red. Okay, so let's do the mean update one more time. Where do you think this purple will move now? This will be one of these points, maybe, if it is exactly in the center.
Yes.
So this would be the purple centroid, the new updated purple centroid. And where would the red come? Red would come somewhere here. Yes or no?
Yeah.
Okay. After this, do you think there will be any new reassignments?
No.
So do you see that when I started this journey, okay, when I started this journey, look at this whole cluster. This is where I started my journey, right?
Yes.
Okay, this was the initial clustering. What can you say about the within distances of the two clusters? Was it high or low?
Within was high.
I mean, you can see that this cluster is kind of well distributed, right?
Yes.
Okay. So if you try to look at these 4:6 pairs, the distances are quite high. For this one, it is quite small though. Okay, for this one, it is quite small though. However, the total sum of the within distance would be very high. So let's say this value was around 50. Okay, so the total within distance sum for cluster 0 and cluster 1 was around 50. Okay, after updating the clusters, what did I get? I get this to be the updated cluster and this to be the updated cluster.
Yes.
What do you think 50 was reduced to? Probably 30, probably 20. Do you see that after every update, my distances are reducing?
Yes.
And after this, was there any changes at all?
No.
No, right? So this is where the algorithm converges. So when there are, so if you think about this, I'll just show you the whole visualization so that you guys understand it. Okay, at least we can see the visualization, right? Okay, so this is where we started. We started with the initial centroids. Okay, these were the original assignments, the red and the blue assignments. The cluster centers moved. Okay, and this is where they came. Okay, now it is typing. Okay, this is what the cluster assignments. Okay, and after this, you again change the assignment. So this is how it looked like. Okay, then again the cluster centers will move. This will move probably somewhere here. Okay, again it stopped working. Okay, so red will move slightly above and blue will move slightly lower, right? Yes or no? Do you see that red has moved slightly above and blue has moved slightly lower? Again, see cluster assignments. This is what the cluster assignments will be. Okay. Again, move the centroids a little. So this is how the centroids move. Do it one more time. This is what it comes out to be, and then there is no change. So if there is no change, can I say that the algorithm stops?
Yes.
Yes.
Okay. And this is where beyond this, do you think the within distance can be minimized?
No.
If it was minimized, then there would be change in assignments, right?
Yeah.
And do you see that what these clustering algorithms are trying to do? They are trying to minimize the within distance, or you can conversely say that they are also trying to maximize the across, right? Okay, that is what is happening. I want you to take a look at this. Okay, initially, what was the across distance for the two clusters that I have drawn, the black clusters? Small, right? Yes or no?
Yes.
But when you transition into these final clusters, this one and this one, the across distance became higher, right? For the 9 pairs that you get at the end, the distance became quite high. Okay, so that's the objective of clustering. Now, I hope you have realized why it is called as k-means, because the initial points that are chosen are the centroid points, the mean points. That's why the name is k-means. Okay. Let's understand even though we have seen through a visualization, let's try to write down what are the steps involved. So there are two alternating steps. There are two steps that you are repeating, right? The first, the cluster assignment, then you update the centroids. Cluster assignment, update the centroids. Okay. So there are two alternating steps. Let's say the first step is start with k random centroids. Yes or no? If you have k clusters, I will start with any k random centroids.
Yeah.
Okay. You can choose it as any of the k points randomly, or you can assign these k points outside the data set also. There is no harm in that. Okay. Step 2 would be, these are the alternating steps. So the first step is find the cluster membership. So using the k random centroids, do you think I can find the cluster memberships? I just have to compute the distance, right? Whichever is closer. So if a point is closer to whichever centroid, I can say that this belongs to that cluster. Okay, that means that you'll be finding the cluster membership for it. And the third step is update the centroids. Okay, the means. Now the question is, what would be step 4? Can I say repeat steps 2 and 3 till convergence? Okay. Till the algorithm converges. Okay, till convergence. We will talk about when do you decide, okay, how do you decide the algorithm converges? Okay. It's very similar to your gradient descent. So there are names, okay, for this. Step 2 is called as the expectation step.
Sanatan, you said find the cluster membership, right? Can you say it once again?
So cluster memberships is meaning that you are assigning every point with red or blue cluster, right?
Yeah.
How do you do that? You look at the distance with respect to the centroids.
Yes.
So you started with some k centroids. Then you have to know which point gets assigned to which cluster, right?
Yeah.
Look at the first step that I drew here. Okay. That
Yes.
started with these two initial points. Okay. 1 second. I started with this was the original red and this was the original blue, right?
Yes.
And then I wanted to know which is the red cluster and which is the blue cluster, right? How did I do that? I computed the distance, right?
Yes.
To the two centroids. That is what I'm saying. So you're finding the cluster memberships with respect to the original, with respect to the centroids.
With this, okay.
Yeah, with respect to the centroids. I shouldn't call it at random because once they are fixed. Okay.
With respect to centroids, okay.
Okay. And then you update the centroids and you keep on repeating these steps till convergence. Okay. So these two alternating steps have a name. So step 2 is called as the expectation step. Step 3 is called as the maximization step. And hence the name of the algorithm is expectation maximization. So this algorithm uses expectation maximization to optimize the values, to optimize the cluster memberships. Does that make sense?
Yes.
Okay. That's the name of the, you can say the optimizer. Okay. This is a technique that is used to optimize the loss function. And what is the loss function if you think about it? What is the loss function? What is it that you're trying to minimize?
Minimize the within distance.
Yeah.
That's the loss function. Okay. So mathematically, what this is doing is it is minimizing the within distance by using the expectation maximization algorithm as the optimization technique. Okay. So when we were trying to minimize the squared error in linear regression, okay, what is it that we were minimizing? The squared error, right?
Yes.
And what was the optimization technique? Gradient descent. Okay. So here the optimization technique is called as this expectation maximization. So it may be asked. Okay, it may be asked. Okay. All right. Okay. So what are the convergence criteria? This is what we have to discuss. So we have also discussed in the context of gradient descent, how does it stop? Okay, how do we decide when to stop? So one idea is, do you think I can repeat the steps for a fixed number of iterations? Repeat steps 2 and 3 for a fixed number of iterations. That was called that maximum ITER, right?
Yeah, maximum ITER, yeah.
Okay. Do you remember the tolerance value in gradient descent?
Yes.
So if I look at the within distance between two successive iterations, If it is not changing much, do you think I can stop?
Yes.
So let's say the distance between the within distance difference between two successive iterations, if it is just changing by 0.001, I can stop, right?
Yes.
So you can assign a fixed value. And if the difference between, so this is the difference between two successive iterations, difference between the within distances of two successive iterations. Okay. Another thing that you can do is, which is kind of the same thing, if you think about it, when there is no change in assignments, what would be the difference in the two successive iterations? 0. Yes or no?
Yes.
Because the within distance will not change them. Okay. So both the techniques, I mean, both the things are kind of equivalent. Okay? Both the techniques are kind of equivalent. Okay. So these are some of the conditions that you could use, okay, to decide when to stop gradient, when to stop this expectation maximization algorithm, and how do you get the final result. Okay.
Can we specify what is the minimum within distance that we require?
Oh, no, that you cannot know, right? Then you're assuming that you know what the optimal clusters are.
Okay.
We want to find the optimal clusters, right?
Mhm.
Okay. The only thing that you could do is note this. Okay. See, when you are saying that you want to specify the optimal minimum distance, okay, what you are essentially saying is, okay, that see here you have fixed clusters, right? For fixed number of clusters, do you think there is a least value possible for within distance? Yes or no? Think again, okay, think again. Let's say this is the scenario. Let's say this is the scenario. What could be the least within distance? Let's say this is, let's say they are parallel, okay? This is parallel, okay? So let's say this is 1, this is 2, this is say 3, this is 4, and this is 5, okay? And let's say this is say 3, okay? What is the within distance right now between these 2 points?
Between these two, it's
So it would be 3, 3, and this would be 4, 3, right? These are the 2 points. I want to compute the within distance. Let's use square distance to compute. By the way, let me tell you, the algorithm uses Euclidean distance. Okay. So, but just to, for the sake of simplicity, I don't have to take the square root. Okay. Or let's take the square root also. There is no harm in that. So, the algorithm uses Euclidean distance by default. So, this would be 3 minus 4 whole square plus 3 minus 3 whole square. And then you take the root of it. This is root 1. Yes or no?
yes.
Okay. What about these two? That will be the same as well. 1 only. 5, 1 and 5, 2. 1, 5 and 1, 2. Sorry, 2, 5. Yes or no?
Yes.
It would still be 1. So what is the within distance sum for the optimal cluster?
2.
2. Do you think it can be minimized?
No.
So you cannot specify it, right?
Okay.
Here you can see visually what is happening, right? So if you say that you want 1, do you think it will ever reach there?
No.
No. So it cannot, it is not possible, right? The only thing that you can do is maybe the initial cluster memberships were like this. Okay. So if you say that the tolerance value is 5, okay, so it will stop at this point.
Yes.
Because if you look at the within distance right now, what is the within distance right now? Take the root. Okay, take the root. Okay. And this would be, so look at these 3 points. So how many pairs would you consider? There are 3 points here, right? 1, 2, and 3. So what is the within distance of this cluster? Can we talk about this first?
Within would be 0.
0. For this cluster, 1 and 0. And within distance for this would be how many pairs would we consider? 3 pairs, right? Okay. So what is the distance between this 1, 5 and 2, 5? We just computed this.
1.
1. Okay. Let's say this is 1. What is the distance between this 1, 5 and say this 3, 1? We can compute this, right? 1 minus 3 whole square plus 5 minus 1 whole square. Does that make sense?
Yes.
So this would be 4 plus 16. This is root 20.
Yes.
Yes or no? Okay. This would be, again, do it with respect to 3, 1. Okay. So this would be root of 1 plus 16. This is root 70. So 1 plus root 20 plus root 17. Root 17 would be almost 4 point something. Root 20 would be 4.3 or something. Okay. So this is 4.1, let's say. So what is the total distance right now? Maybe 9.4.
9.4.
Okay. Let's say if I put the tolerance as 10, do you think it will go further?
No.
No, right? It will stop here itself. Okay. It will stop here itself. Okay. Because the within distance. No, I shouldn't say the tolerance. It should be the minimum. I mean, if you put the condition on within distance. Okay. If this is what you are expecting, okay, it will just stop here. All right. So it makes sense to do tolerance, right? So after this, if you go to this stage, okay, after this, if you go to this stage where you reach this and this, so you have reduced the distance from how much? 9.4 to how much? To 2, right?
Yes.
Okay. So what was the change between them? 7.4.
Yes.
So if your tolerance is 0.001, this is okay, right? This is acceptable. So you will go further, right? So when you reach to this stage, you will try it one more. But after this, is there any change?
No.
So 2 will go to 2 again. So what is the difference between them? 0, which is less than 0.001. So it will stop.
Okay.
Okay. That's what this is. All right. So these were the convergence criterion. Okay. For this. Let's see some limitations of this algorithm. So one of the limitations of this algorithm is it is highly susceptible to initialization. When I say highly susceptible to initialization, do you think that if I would have initialized the clusters, I mean the points randomly, assign the points randomly to any cluster, do you think it would take more iterations or less iterations? I hope you have realized by now what is happening.
Yeah, if it is random, then more iterations.
Right? Okay, that makes sense, right? Okay. Another thing is, do you think that if I give a different initialization, will it always end up in the same clusters?
No,
Yes.
sorry.
Yes. Yes.
No.
No, right?
Yes.
Can you give me an example where it ends up in different clusters? It's very hard to do, by the way. Most of the time, it will end up in the same clusters. I'm going to show you an example, a simple example, where I'll show you that if you unluckily give a bad cluster initialization, okay, it can end up in a scenario where it will not go any further, okay, and may give you different results with the different initializations. Shall we do one such example?
Yes.
Okay, just to
So
show.
you're saying that, like, if I'm giving in initial centroid as
So let's
incorrectly.
red and you cannot say incorrectly because there is no correct way of doing it, right? So, but the idea is, let's say if I start with some different value for red and initial blue,
Okay.
okay, you might end up in a different scenario altogether. Different clusters would be obtained. That's what I'm saying. And you may feel like, no, it will always converge to the same results. No. Let's see. That is what I'm going to demonstrate now. Let's say there are 3 points which are equally distant. Okay. So this is 1, this is 2, this is 3. They are equally distant. Okay. You start with, say, maybe say black cluster here. You can call it black cluster. And this is, say, blue cluster, maybe here. So which point will be black? Only this one, right? These will be blue and this will be black. Does that make sense?
Yes.
Okay. Makes sense or not? Now, where will blue shift? So blue will shift slightly here in the middle. And where will black become? Black will come on top of this. Do you think after this there will be any change?
No.
Okay. So these are the 2 clusters that you are having. So let's call this as cluster 0, this as cluster 1. So point 1 belongs to 0, point 2 belongs to 0, and this belongs to 1. Does that make sense? This is your cluster membership? Yes or no? Is this clear? Can you say yes if that's clear?
Yes.
Okay. Now again, take the 3 points. I hope you have realized by now, okay, it will be different. If I give, say, one cluster here and maybe say one cluster here. This will be one, this will be one, this moves here, this moves slightly to the middle. And what is happening now? This is a 0 and this is 1, 1. Yes or no?
Yes.
Okay, so it can give you slightly different results, but see the magic. The magic is what is the within distance for both of them,
It's same first.
right? What is the total within distance? 1 only.
Mm.
See, for this cluster, what is the within distance? 0. And what is the within distance of cluster 0? 1. What about in this case?
0, 1.
So this is within clusters, this is 0 and this is 1. Do you see that the sum of within distances stay the same? But you can get different assignments. Does that make sense? Okay. All right. Now, let's say you stopped without reaching the tolerance values. So this is also one condition, right? Max iteration. So you can stop even before reaching the tolerance, right? Yes or no?
Yeah.
You have a huge data set and there are a large number of iterations that you require. Okay, but you don't have that much time. So you will stop somewhere, right? So you started with some initialization, you got some clustering. Okay. You have you did another initialization. Okay. You got some clustering after 10 iterations. Is it possible they will be different? Quite possible, right? Yes or no?
Yes.
Not reach to the optimal clustering, it is quite possible that the results would be different. My question is this: which clustering out of the two will you choose? Which clustering out of the two will you choose?
Can you repeat the questions?
See, so I'm putting this condition of max iterations. This is there by default in my implementation, right?
Yeah.
Tell me, when would the algorithm actually converge? When this is met or this is met? Whichever is met first, don't you think that will stop?
Yes.
Okay, let's say I have reached to a stage where iterations are exhausted. Let's say this was 100. Okay, but maybe at the end of 500 iterations, I achieve this level of tolerance lower than this. So I should have run it for more iterations, right?
Yes.
Yeah.
Since I'm fixing it to 100, okay, I will end up in one clustering.
Yes.
Does that make sense or not? Okay.
Yes. Yes.
It's not a good clustering. Okay. Again, I started with another initialization. I ran 100 iterations. It did not converge. So the results can be different.
Yes.
Yes.
The previous one. I'm saying that how do you decide which one is better of the two? It's a simple question.
Whichever I get the minimum within distance.
Within distance. Yeah.
That is the answer to this. So the idea is, like, when you see the implementation of k-means, right? What it will do is it will do the initialization 10 different times. We'll get the cluster memberships for those 10 different times after exhausting the iterations or whichever is met first. If it is iterations or tolerance, whichever is met first, it does it 10 times and reaches to a cluster membership. And then how do you select like between all the 10s? Use that one which has the minimum within distance.
Minimum within distance. Okay.
So what it does is, if you have discarded, so you ran for the first one, you got some within distance, right? Then you start with the new initialization, got the within distance. If it was lower, you can discard this, right, already.
Yeah.
So you don't have to keep track of it. Just discard it at that moment itself. Okay. Then you do another initialization, find the membership. If it is already lower, just keep this. Okay. But if it was lower than this, you keep that, the new one, and you do it 10 times. Okay. So this is how the implementation does it. It runs it 10 different times. Okay. Keep that in mind.
This 10 number is fixed or that? Yeah,
You can change it. But by default, the number is 10. Okay. For bigger data set, you should reduce it, by the way. Okay. Otherwise,
Even at 10 times I have to reduce.
yeah, why not?
Okay.
I mean, if you want to run more, increase the max iterations. I mean, you run it once, right? But run it to the fullest.
Okay.
Again, there is a catch, right? The tolerance and the max iterations, they are interlinked. Whichever of them is met first, it will stop there, right? But you don't
Yeah.
know when will be met first, right? What if you cannot even visualize the data?
Okay.
Does that make sense? Okay, because you
So
have
instead of
the maximum solution, right? The best solution.
instead of initializing the value 10 times, I can increase the max iteration so that I can end up in a good
Or
shape.
the tolerance also.
Okay, so I'll meet the tolerance.
The question is, would you know by how much I should reduce it? Would you know how much to increase the iteration so that you would not want to run it forever, right?
No.
There is a thing, right? There is a thing which can happen, right? So you have to stop somewhere. Okay. And another advantage that you have is, do you think that I actually know what are the optimal clusters, the ideal clusters? From the data, do I actually know what are the ideal clusters?
Yes.
How would you know that?
Got the data.
How would you know that by the array? Come on, I just asked you this. If for more than 3 dimensions, how would you know? Would you ask a manual labeler to do it?
No.
No, right? If I give you 5 million examples in 4 dimensions, can anyone do it for you? No.
No.
Is that intelligent also? Okay. So I don't have, see, this is called as unsupervised learning. Is there any ground truth? That's the first question. Is there any output as such that I have with the help of which I can compare? See, in classification and regression, you knew the actual outputs, right? So you can see how good the algorithm was doing using accuracy, precision, recall. In regression, you use mean squared error, R2 score, and all that. Can you use it here? Think. No, right?
No.
I don't know the ground truth. That's the big thing. Okay. So how do we evaluate the model? That's a good question. Think. How do you evaluate the goodness of my model? How do I evaluate the clustering algorithm?
When it comes to clustering algorithm,
Like the same thing, like if I have clusters with minimum within distance, I'll go like
So the
that.
only thing that you can do is look at distances, right?
yeah.
Between the clusters and within the clusters.
Yes.
But there is no ground truth as such. Please remember this. There is no actual thing as such in this case. So the only thing that you could do is you can look at the distances between and within the clusters to say, okay, it is a good clustering or a bad clustering. And all the clustering evaluation metrics are doing that in some form of within distance or across distance or both of them. So the clustering evaluation metrics that we will see, they will only try to look at the within or the across distance in some way. Okay. Is there an understanding now? Yes, sir. Do you have clarity on how the clustering evaluation metrics will be designed? So it will not be, because there is no actual value as such, right? The only thing that I can do is I can measure the distances, okay, at the end.
Okay.
So that is what you will see in clustering evaluation metrics. We'll talk about that tomorrow. I need a lot of time, maybe 1 hour to discuss all of those. Okay. Okay, a few more things about this algorithm, and we have to discuss the remaining ones as well, by the way. Let's say I'm trying to plot a curve for number of clusters versus within distance. Okay. How many maximum number of clusters can you make?
Number of samples.
Number of samples. Okay. So if the number of samples is n, okay, if the number of samples is n, what would be the within distance?
0.
0, right? Because every sample will be the mean.
Yes.
Yes or no? Every sample will be the mean, right? So there is no pair, right, to compute that distance from. Okay. But what will happen if you have just 2 clusters? Will it be high or low, the within distance?
High.
What do you think? If for 3, it would be even higher or lower?
For 3,
It would be even lower, right? Because for n, where do you reach? You reach to 0, right?
yes.
Okay, so this will always go down. Okay, this will always go down. Yeah, I made a bad figure like this. Okay, I'll just make it like this. Do you think, is there a need to do it for 1, by the way? 1 means that basically total pairwise distance. Yes or no? 1 means a total pairwise distance, right?
Yes.
Okay, so let's say this is the maximum. If you do it for 2 clusters, you have partitioned your data into 2. So now you have smaller sets, right? So the within distance would reduce. Within distance does not include the total distance, okay? Within distance is only the within distance, okay? So this will always go down if you think about it. So I'm just going to make a plot like this. Okay. Can you tell me beyond which number of clusters the within distance is not changing much? After what value?
After 4, I would say.
So this point is actually called as the elbow point. So since I do not really know what are the good number of clusters, right? But somebody can ask me, what are the good number of clusters, right? I can train with 2 clusters, 3 clusters, 4 clusters, 5 clusters. I'll go up to 0. So how do I know what are the ideal number of clusters? This is one way to determine it. Reach to a point beyond which the within distance is not changing much. This is also called as the elbow point or the knee point. Okay, so if you look at your elbow, okay, do you think you can lower it any further beyond a certain limit?
No.
No, right? That's why it is called as the elbow point. This is also called as the elbow curve or the knee curve. So with the help of this curve, you determine the optimal number of clusters. You determine the optimal number of clusters with this. Okay, and we will study clustering evaluation metrics also. With the help of those also you can do it. But for k-means, this is the ideal way. In the literature, everyone prefers this. Okay, this is called as the elbow curve. This is how you determine the optimal number of clusters. Okay. Now,
so first we determine with using this, we determine determine the number of clusters which are optimal for me to use in the algorithm, and then I put those k values in my algorithm to see which combinations give me minimum within distance.
No. See, minimum within distance I'll get at n, right? Which would be 0.
Yes.
All I'm saying is this. See, if you say that every point is a cluster, then what's the usage of it?
No usage.
No usage, right? So the idea is I want to put samples into some decent number of clusters, right? Not too high. Okay. So if I can find a number of clusters beyond which the within distance does not change much, can I say it's a decent clustering?
Yes.
Because I have identified a good number of clusters, right, where most of the samples belong to, beyond which the distance is not decreasing much. That is why I'm saying this is like the optimal clustering for you.
Yes.
Use those 4 clusters to make suggestions. Okay. So ultimately, you can say that if 2 points are belonging to the same cluster, they are more similar. Okay. Does that make sense now?
Yes. So that's what, like in k-means algorithm of clustering, we have to give how many, first is how many random points we are taking, whether it's 2 or 3, that tells us how many clusters we'll be.
So see, this plot that I'm making is when you give 2 clusters to k-means. Okay.
Yes.
K-means will return you the best cluster membership, right?
Yes.
The best cluster membership, this is the within distance. Now give 3 clusters. Start with 10 different initializations. Find the best cluster membership with 3 clusters. This is the best cluster membership, the best within distance for the 3 clusters. Okay. When you start with 4, so start with 10 different initializations of 4 clusters. Find the best cluster memberships with that. Within distance for that. I'm saying that when you do it with 4, okay, you are getting a good value for the number of clusters. You start with this. You use this for your suggestions. You use this for your applications.
Okay.
Okay.
So,
see, k-means cannot tell you what is the ideal number of clusters, right? If you think about it, because you are pre-specifying it, right? How do you use this algorithm to determine the optimal number of clusters? You use this curve. Okay. You use this method. Does that make sense?
Yeah. So first we use this, determine whatever, how many clusters will give me optimal results, and then we use that value of clusters in my k-means algorithm to give me best
Memberships again, and so depending on the cluster memberships that you obtain, right, you figure out this similarity between the people or the whatever the samples are, okay, and build applications on top of it.
Yes.
Okay. All right.
So when it comes to 2 clustering or 3 clustering, I need to initialize it once again. Like I need to run my
times each at least.
What is it?
The algorithm will do it 10 times for you. Will find the best memberships from those 10 times. store the one which has the least within distance, and that is the within distance that I'm plotting here.
Okay.
Okay.
So after a while, when the clustering value is not changing, that time I stop it and then I call it as elbow.
Now, again, see, you are missing the point. Can you do k-means with two clusters? You can, right? How does
Yeah.
k-means work? Okay, do it just one time. Do it just one time. You start with 2 points.
Yes.
You will get some cluster memberships, right? You will
Yeah.
be doing some iterations, right? You
Yes.
so you will get some answer of your cluster memberships, right?
Yes.
This answer optimal? No, right? So it's not guaranteed to be optimal, right?
Yeah.
We just discussed it a few minutes back. So to avoid this, what we do? We run it 10 times. So maybe when we started with this point, this was the result. Let's say I start with these 2 points. I'll get some other result, right?
Yeah.
Maybe I'll get this result. So can you start with 10 different times, get the 10 results, and
Okay.
score the one which is the best? What would be the best result with the least within distance?
Least. Yes.
So store the result with the least within distance, and whatever is the least within distance, I'm plotting here
Okay.
for k equal to 2. Okay. Can you repeat the same thing for k equal to 3?
Yeah. Yeah. Yeah.
Okay. So elbow curve is essentially looking at the best of the bests. Okay. So it is there to determine best among the best values for all the individual number of clusters. Okay. And then I'm making a claim, which is the best value that you should actually use in your applications. Please remember this. Okay. So see, one idea is you want to use k-means when you have fixed number of resources, right? Then you don't do this experiment. But sometimes you may want to know, okay, think about this. Let's say you have ideally 4 clusters in your data. You had the budget for 6 coffee machines. So would you install 6 coffee machines, or just 4 would do? 4 would do, right?
Yeah.
Yes, sir.
Yeah.
Why would you go for extra money? You're not a fool, right?
Yes.
Nobody is, right? So they would also like to know what is the ideal number of clusters, right, in the groups in my data. So they'll stop at 4. Why would they spend extra money? Okay. But if it is less, let's say if it is less, let's say if it is 3, then you stop at 3 if you don't
Okay.
have for 4. Okay. I hope that makes sense. Okay. All right. Now, okay, I just need 2 more minutes. So k-means is another has one big issue. The one big issue with k-means is it cannot identify non-convex clusters. It cannot identify non-convex clusters. So like this. So imagine this is one cluster and this is one cluster. Do you think k-means can identify this nicely?
No.
Why? Well, I said it initially, right? But why?
If it will take the center, like the center of the first C curve and the reverse C curve, but
So
topmost point.
let's say this is the center of the first C curve. Okay. So if this is the center, what do you think? This point will be purple or not?
Purple.
Yeah.
Are these in the same clusters?
No.
Misclassifications will happen. Like,
There is no misclassification concept here. Okay. But all I'm saying is that either it will give you these 2 clusters, or it will give you these 2 clusters. Okay. Or it will give you these 2 clusters. Yes. It depends on where you started, right? Okay. So cannot work with non-convex clusters, especially if the shapes are kind of highly convoluted. Okay. They are kind of overlapping. Okay. One more thing, is mean always a good representation? Okay, think about this. Let's say if there is a data like this. Where do you think the mean would lie? Here, right?
Yes.
The mean is lying outside the data, if you think about it. Is it a valid way to choose the representative for your cluster?
No.
No, right? Let's say you have you have the samples as integers. Mean can be a fraction, right? So a fraction value a good representative for integers.
No.
No, right? So what do you do then?
I take ceiling or floor, whatever.
You do that, right? Okay. Can you suggest? Can you think of something else? A good representative for your say integer data. The value. Okay. How do you define the mean? Average, right?
Yes.
Okay, can you think of something else?
Median.
Median. Okay, so there is an algorithm. I understand that what you're saying. See, maybe the next closest integer value is not in your data. So you cannot choose that as a representative, right?
Yes. Yes.
Okay, I'm saying that, see, mean can lie outside the data, right?
Hmm.
It may not be one of the points. So sometimes I may like to choose one of the points as the representative point, right?
Hmm.
To represent my group. Okay, so if you are doing these experiments, you go to say, okay, you want to find who should be the representative of a group. So in that case, you want one of the individuals to be the representative, right?
Yes.
So how do I choose which point should be the representative? You cannot just take the mean and the closest to the mean, right?
Hmm.
So mean may not be a valid person. Okay.
Yes.
Mean may not exist at all, right? Okay. So in that case, you choose median. And if you choose median, the experiments remain the same, everything, but the name of the algorithm is k-midioids. Okay. Do you think that k-midioids will also give you good results here? No. But the representative would be what? One of the points. That's it. So maybe one of the representatives would be lying here. Okay. And one of the representatives would probably lie here. Sorry, would lie here. Does that make sense?
Will that top X representative that you have said, won't it lie on the
Cluster.
first C curve?
Clusters. Black cluster. I'll highlight those clusters. Okay. This is the red cluster. So the representative of this would be this point. Okay. And if this is the say blue cluster, the representative would be this point, the middle. Okay. Make sense?
Yes.
Okay. So this is k-midioids. All right. This is one thing that I wanted to discuss. So k-means cannot do non-convex clustering. So we'll see all these experiments in the next class. We will also see what are the other algorithms and how they improve upon k-means, or how they overcome some of the challenges with k-means. By the way, this is the most popular algorithm out there. And one more thing is, do you think this can determine outliers? No, right? Can it determine outliers?
Or to try to accommodate the outlier within any of the clusters.
Right. So you don't see any outliers with this algorithm, right? But think of this. Let's say this is one cluster. Okay. This is possible, right? This could be one of the clusters. Okay.
Yeah.
Maybe other cluster lies here. Okay, like this. Obviously, these would be the two clusters, right? Yes or no?
Yes.
Now, my question is this. You know that, okay, this point seems like an outlier, right? How would you identify it?
The within distance of this cluster is very high.
No, but this is the least within distance that you get, right? If there was a better clustering, you would get a different result, right? If there is a better clustering, you would get a different result. This is what you get
Yes.
the value, okay?
It will run 10 times, right? Okay.
Think about this, okay? And maybe I'll just keep it like this. This is the centroid somewhere, yes or no? Now maybe it can give you a hint. Look at the distance of the, you can say that so if you want to know if a point is an outlier or not, look at the distance of that point from its centroid. Okay. Can I say that if this distance of this sample with respect to the centroid, if it is much more than the average distance of all the points with respect to the centroids? Yes or no?
Yes.
Okay, so you can put a threshold, right? Like maybe say C into this average distance. If C is say 2.5, if the distance is more than 2.5 times the average distance of the other points, I can say it's an outlier, right?
Yes.
You can put C value to be anything. That is one way to change this algorithm to determine outliers. This is one implementation there in PYOD. Okay, I'll show you one more. Okay, all these things we have studied, by the way. Now use the concept of nearest neighbors. So think of this point. Let's say you want to know if it is an outlier or not. So you look at the nearest neighbors. Okay, these are, say, I'm looking at 3 nearest neighbors. So these are the 3 nearest neighbors, right? Yes or no? You sum up the distances. Okay, maybe for this point, these would be the nearest neighbors. Carefully see. What do you see about the sum of the distances of the nearest neighbors?
For outlier, it is very high. And
So use that concept. Okay. So if the sum of the distances of the nearest neighbors is very high, maybe say 3 times or 4 times more than the average distance of the nearest neighbors for all the other points, can I say that it is an outlier? Yes, right?
Yes.
So whatever algorithm that you have studied in the past, right, can be leveraged to modify any of the clustering algorithms to determine outliers. So these are the important, you can say, extensions, and they have implementations in PYOD. Okay, so do check it out in your free time. It's a very easy library to use. Format is same as sklearn, fit, predict. Okay, all right. I'll stop here. We'll meet.
So you're
yes.
saying that like there is a 2 clusters. So like if the distance of an within distance of an sample was too high, like the distance from the centroid of
How can we see again? Don't use incorrect terminology.
okay.
You never say within distance of a sample. Within distance is for a cluster. Now tell me what is it that you want to say.
Okay.
No, say. Now I know you wanted to say something. I'm not discouraging you. I'm just trying to say, ensure that when you go for an interview, right, you don't speak that way. If you do that, you'll be rejected. Okay.
Sure.
Yeah. Now let's try to discuss what is it that you were saying.
Yeah, the distance between the centroid and the outlier you said, right? So if the distance was too high, then like it'll automatically impact.
The within distance, right?
Yeah.
The total within distance of the cluster. It will, right? But I do not know what is a good within distance or a bad within distance, right? If I have obtained this would be the idealistic within distance, right? Because if there was a solution which was better than this, I would have obtained that.
Okay.
Think about this. If there was a better solution than this, I would have obtained it, right? This algorithm does not exclude outlier points. It keeps every point in some group. Okay. So every point will fall in a group. Now I'm saying that within a group, there might be outliers. So you can use the concept of nearest neighbors. You can use the concept of distance with respect to the centroids to identify outliers.
Okay.
Okay. So this can help you eliminate some of the points, okay, which are distant within a group. Okay.
Okay.
You can actually think about it. If a point doesn't have any nearest neighbors within a limit of distance, that can also be an outlier. Yes or no?
Yeah.
It's the same concept. It's said in the reverse way. So if you don't see any points at a distance of 1, that point is nowhere close to others, right?
Yes.
Okay. So these are the extensions that are there that you can use. Okay. Anything else? My iPad has become shit. Okay. All right, let's meet tomorrow and we'll discuss the implementation of this. Before that, we'll discuss the pending algorithms and we'll see evaluation metrics. And then we will do the implementation of this. So this week and hopefully the next week, we'll be able to cover up everything. I don't want to go beyond the next week. Okay. We'll keep one session for all your doubts. Okay. So you can, for the next week, I'm just announcing it again. Thursday's class will be the doubt clarification class. Any other doubts that you have, please bring it. Okay. So do this. Okay. All right. I'll see you in the next class. Goodbye. Bye, everyone.
Thank you, Sant.
Yeah, I'll upload this in your drive folder and the slides as well so that you can view the
Clustering illustration.
visualization and some other details are also there in the slides.
Okay.
That we'll discuss tomorrow. Okay. So goodbye. Bye, everyone.
Bye-bye. Yeah.